I wanted to show how you can use Excel formulas to recognize handwritten digits. So here's a digit that I've put into an Excel spreadsheet. It's a number 3, and we want to try and work out using Excel how we can identify that digit using a neural network. So we're going to use the MNIST set of digits, which is quite a common database of handwritten digits. If you just Google MNIST, it's kind of hosted here by a guy called Jan LeCun, who's a kind of bit of a legend in the neural network and image recognition world. You can also see down here there's some samples of the digits. There's quite a lot of digits, and here's quite a lot of information about it. And here is where I downloaded the digits in comma-separated variable format. So that's where I got the data from. I then simply put it on the screen here. I've got in here a training set and a testing set, which is what I've downloaded. And basically each image is a 28 by 28 pixel image. And the first digit in here is the actual number, and then there's 28 times 28 equals 784 different digits representing the grayscale of the image. So you can see that some of them have got zeros, which basically means it's white, and then there's some numbers that are getting up to the 255 mark, which represent black. So if we go back to the control tab, you can see here what I've done is I've kind of taken this string. I've randomly brought one of the values onto the screen. So this is row number 2835, and it's a random number between 1 and 60,000. I've then split that down into its constituent parts and put it on the screen, and then used some conditional formatting so that you can actually visualize the image. So these are actually pixels which are filled in with the numbers from here. So what I wanted to do is create a neural network to identify this digit. So the neural network is going to live in this tab here, and I've already brought in these numbers. So here I've got 784 numbers that I've brought in from the other tab, and basically I've divided by 127 and then subtracted 1, so I get a number roughly between -1 and 1. And if I page through it, you can see where there's numbers that represent the darker part of the image, and -1 where it's white. So with a neural network, we generally keep things between -1 and 1. So the format of my neural network, I'm going to have a number of hidden nodes, and I'm going to have a number of these, and I'm going to go for, I don't know, 30 or so. I can let me go. 30 hidden nodes, and then I'm going to have 10 output nodes. Actually, I'm going to number it output 0 to output 9. So the input nodes are the grayscale image. The output nodes are going to be indicators to say whether that image represents a 0, a 1, a 2, up to a 9. And what I'm going to try and get the neural network to do is put a big number in the correct node for the number that's represented. So ideally, if we're looking at a number 3 here, what I really want to happen is that all these have noughts in them, and the 3 has a 1 in it. So that's what we're going to attempt to do. Now, the way a neural network works is you don't have to have a hidden layer, and you can have multiple hidden layers. Generally, you have at least one hidden layer. And what we do within a neural network is we link each of the input nodes to each of the hidden nodes, and then we assign a weight to each one, and we multiply the weight times the input node, and we add those all up together and then sum it. So we sum it into the value for there. So then we take all the weights that link the input nodes and hidden 2, multiply those together, and we get the the value for node 2. We then do the same thing here, that we have a weight that links the hidden 1 with each of the 10 outputs, hidden 2 with each of the 10 outputs, and so on until we've kind of calculated all those. So effectively what I need is a matrix which is 784 by 30 with a number of weights in to link those two, and then I need another matrix which has 30 times 10 weights to link each of the hidden neurons to each of the output neurons. So I'll just get rid of this so we can start again from scratch. So first off, I'm going to create that matrix, which I need to be 784 wide. So to get that, I'm going to just do paste. I'm going to transpose this. So you didn't quite see that. Again. So I've just transposed that over here. So now I've got 784 columns across the top. And then hidden 1 30 times down here. So there I've got a matrix of 784 by 30. So then I want to fill that in with random weights. So if I do rand times 2 minus 1, the rand gives me a number between 0 and 1. So times in 2 multiplying by and subtracting 1 will give me a number between -1 and 1. So I can paste those in there. And that gives me random numbers, 784 times 30 random numbers representing those weights between the input neurons and the hidden neurons. So they don't change every single time. What I'm going to do is I'm going to do, again, copy, paste the values. So now, instead of having a formula, I've just got those weights. Okay, so that gives me my weights. I then need all my hidden neurons, right? So these are my hidden neurons, and as I said, what I need to do is calculate each of these weights times each of the input values to calculate the value for the hidden neuron number 1, and the same thing here. And I can do that with a very useful function called mmult, which is a matrix multiplication. Slightly different to anything you might have used before, and what you actually have to do is to highlight the whole range of cells that you want to do the matrix multiplication and say equals mmult, open brackets. My array 1 is this array here, and I want to multiply that by array 2, which is actually this vector here. Those brackets. Now, because it's a matrix formula, I actually have to do Control Shift and Enter to put that value in, and you can see it then puts curly brackets around it, and basically it's done a matrix multiplication of this matrix, this big matrix here, times the input neuron matrix to calculate these weights. Calculate these outputs. So this is just a sum of all the inputs times the weights for hidden 1. And this is the sum of all the inputs times the weights for hidden 2, hidden 3, and so on and so forth. So that's calculated the input to the hidden neuron. What we then generally have is a bias, and the bias again is just a random number between 0 and -1. Which I add in there, and then I just simply add in, the two together. just do the same thing to get rid of the formulas here. So copy, paste, values. Just copy that down. I should point out that I've actually got calculation switched off, so that's why I have to keep pressing F9, because I don't want it to recalculate just every time I hit enter. So I've got manual calculation, enable iterations and iterations of 1. That means that every time I hit F9, and any time I've got a circular function, it means it's just going to iterate once around all the circular functions and repopulate everything just once. So that's why I'm having to press F9 to make the values work. So there we go, we're off and running. We now need to apply what we call the smoothing function, and I'm going to use a logistics function called a sigmoid function. And basically what this is going to do is it's going to keep these values within a restricted range, in this case between 0 and 1. So what I'm going to do is I'm going to use a function which is equals 1 divided by 1 plus e to the minus that. I'm going to paste that down there, and that's going to be my activation function. So you can see any big numbers are coming out as kind of very high numbers, and any very negative numbers are coming out as very small numbers, and they're always between 0 and 1. And I've just done a little test here to show you. So I've got the value -5 to +5 here, and I've got this same sigmoid function here. And if I just highlight all those and do insert scatter graph, simple scatter graph, you can see that's the graph of these numbers between -5 according to the sigmoid function. You can see it's like an S, which is why it's called a sigmoid. And you can see that if a value of 0 comes in, it returns 0.5. And the bigger the number gets, the closer it tends to 1, and the smaller it gets, the closer it tends to 0. So that gives us the sigmoid function, the activation function. So we go back to our neural network. So effectively this now represents this is the sum of the weights times the inputs plus the bias. The bias just helps with the activation of the neuron, and the sum of all this plus the bias gives us the net. We apply the sigmoid function to get the output of the neuron. So this, if you like, all this here is one neuron. So this is the first hidden neuron, which has got the summing of the weights times the inputs plus the bias, and then smoothed according to the sigmoid function. So that gives me the starting point. I now need to have, as I said, a set of weights that link each of these 30 hidden neurons to the 10 output neurons. So we need output 0 to output 10, output 9, because it's 0 to 9, and then I'll just do the same thing again. Just paste that into here. Transpose, which gives me the right size matrix. So then I just need to do the same thing again. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10. That gives me a nice matrix of 10 by 30, so 300 weights. I need to paste those values in again, so I don't get those changing every time I do anything. So that's my weights linking my hidden neurons to my output neuron. So I just need to do the same thing again as I've got here, right? So I need to multiply sorry, it's a bit flickery. So I need to say equals, sorry, remember highlight the whole range first, equals mmult. Array 1 is this weights array. Array 2 is the output of the hidden neurons. Shift Control Enter gives me those there. So that gives me the sum the weights times hidden neurons. And then I'm just going to do the same thing again, right? I'm just going to add in a bias, sum it up, and then apply the sigmoid function. So I'm just going to copy all that and paste it here, and then copy that down here. Now, just for completeness, I'm going to redo these so that they're different random numbers to the hidden neurons. There we go. So again, I'm going to copy the titles again. So this is the bias. This is the net, and this is the output. So that's simply the sum of the weights times the hidden neurons. There's a bias. I add in the bias and I apply the sigmoid function. So what I need to do now is, what I said was that what we wanted to do was to take the highest value that was here and assume that that is what the neural network thinks the number is. So what I'll do is I'll say equals max each of those. So that'll work out what the biggest value is. And I'm going to say equals if that equals that, comma 1, comma 0, which basically should say that the highest values there. Okay, generate that's a bit of this. I need to fix these values because otherwise it's not going to work. Because at the moment this one's shifted down and this one's shifted down. Okay, so if I do that, so now they're all the same and it should be picking the highest value. So let me just put numbers 0 to 9 in there. Not to 9 in there. I'm going to say equals that times that. So now, remember, every time I click F9, it should give me a different number. Unfortunately, it's always thinking it's number 7. Oh no, sometimes it thinks it's something else, right? But now I can work out, I can say equals max on that will give me the output. So here we are, we've now got a neural network that's trying to predict the value of the digits, and what I can do is I can call that, I'm going to give that a name, I'm going to call that, what should we call it? Answer. So if I go back to the control here now, I can replace that with equals answer. Oh, it's got that one right. If I do F9, it's generally thinking it's a 2. Now, obviously, we've just got random numbers in our weights, so it's pretty much random what it's doing. What I've got over here is some counters of how many times we've kind of been through assessed a number and whether we've got it right or wrong. And if I kind of just do that for a few, obviously it's pretty much guessing, so you'd assume that it's going to get 1 in 10 right. So if I just do 100 or so, it's doing reasonably well because it's actually at 12%, but it's pretty much guessing what the right answer is. But what we've done so far is that's what's called the forward pass of the neural network. We've worked out the output of the neural network based on these random weights, but obviously they are random. We need to try and work out how we can improve those weights and make them better at estimating what the output, what the number is. So what I'm going to do is I'm going to say, I'm just going to bring into here equals that, which is what the actual number is. Okay, so that's the. Actually, let's not do that. Let's do it this way. So that's what the answer is. So if I say equals if that equals that, remember to do, oops, comma 1, comma 0. So what I'm going to do now is to say that, let's call it the target, that's a better word for it. There's the output and there's the target. So basically the actual target is a number 1, so what I'd really like is to have a 1 in here and zeros in all the others. But what it's actually doing is it's predicting a 9 because it's got a 0.8 here, right? Which is not very good, and it's got a 0.2 there. So what I really want to do is making this number much higher in this scenario, and all these other numbers much lower, in particular this one here because it's got that one wrong. I should have said I've actually used the sigmoid activation function here just for simplicity because it makes the explanation a bit easier because I'm using the same one as in the hidden neurons. There are better activation functions that you can use. The softmax one is often used when you're trying to work out 1 out of a number of values, but we'll just stick to the sigmoid function because it's simpler. What I'm going to do now then is I'm going to calculate an error. I'm going to say that error equals 0.5 times the difference between the target, the output, to the power 2. So basically this is kind of the square of the difference, and that's going to calculate my error. Is that right? No, it's not that one I want, it's this one here I want. Okay, so what I was hoping for this, I was hoping this to be a 0, but the neural network's output 0.6. So what I'm going to do is I'm going to take the difference between the two, square it and multiply by 0.5. And I'm going to do that down here. So basically what we're saying is, in this case, the error is 2. So if you keep doing F9, it's going to bring in different numbers, but that's the error that's calculated. So what we really want to do is, in order to make this better at predicting the number, so it's outputting 9 when it should be outputting a 3, it's calculating the error for that. So what I want to do is work out how we can reduce this overall error so all these numbers get closer to what they should be, and drive this error down, which will improve greatly the accuracy of the neural network. So that's what we need to do next. So let's have a look at how we do that. So what we need to do is work out how we can improve these weights in order to reduce this error. So let's take one weight. Let's take this weight here. This is the weight that links. This is the one that links hidden neuron 30 and output neuron 0. And what I need to do is to work out whether that needs to go up or down. So it's 0.5 and the error is 0.024. So if I make that slightly bigger, so if I make that 0.58. So watching down here, 2.04, 1.59. So that improved it, right? So that weight needs to go up. Right, if I do the same thing and make it 0.56, the error goes up, right? So really what I want to be doing is making this weight go down. Now what I could do is I could do that for every single weight, fiddle around with each one, push it up and make it and see if it makes it better. If not, make it go down a little bit. And I could do that for all the weights, calculate everything through. But every time you put the weight in, you have to refresh a certain element of the network. So there's a better way of doing it. And the better way of doing it is to calculate the gradient of this error in relation to this number here. And in mathematical terms, that's working out what the partial derivative of that number here in relation to this number here. And if we think about what happens to this number here gets multiplied by the is the hidden neuron output of the hidden neuron 30 multiplied by this number, added with all the other calculations, adding in the bias, applying the sigmoid function, and then adding it in there, squaring it, squaring the difference, multiplied by a half, and then summing it up into there. So quite a complicated formula to go from there, through here, through here, through here, through here, into here. And what we need to do is calculate the total gradient of that value into here. Now it looked quite a daunting prospect because we've got quite a few calculations, but what we can do is we can apply something called a chain rule, which basically means to work out the gradient of this with respect to this, is we can work out each of these steps, work out the gradient of each of those steps, multiply them all together, and it will give us the gradient here. So we can do that, right? So what we're going to do is we're going to pretend all these other weights are fixed. The only weight we are interested in is this one here. We're going to assume all these are constants, and this is the only variable. So we've got a big formula now with an awful lot of constants and only one variable that we need to differentiate. So let's start from here. If we go back from here to here, this total error is basically this error plus a load of other errors which are all constant, because we said all these other weights are constant. This is the only value that this weight influences, so all these are constants. So if I differentiate this with respect to this, I get 1. Good. So now I need to go back from this error. This error is based on this, and it is basically and this is based on our weight. So I need to differentiate this now with respect to AFB2. Right, now I'm not going to focus too much on the differentiation, but if you differentiate this with respect to AFB2, because it's squared, the power rule says you reduce this down to 1, multiply this by 2, you have to take the minus out, which means the differential of that, which I'll put down here somewhere, I need to put it in 32, because we're differentiating this bit over here. Let's stick it in here. So we said it was, that goes down, that 2 multiplies by the 0.5 to wipe that out. That minus comes out, so it's minus AFG2 minus, we'll take that, say in here, 32, it's minus that. Okay, so basically what I've done is I've calculated that, I've differentiated that. You can check my calculation if you're interested. I've just then worked out what that value is, which is minus the target minus the output. Okay, so I then need to differentiate this piece, which is a bit more complicated, but it's not hugely complicated. Again, it's basically we need to differentiate with respect this time to this value here, which is AFA2, and it's a bit more complicated to differentiate. But the interesting thing that comes out of that is the formula to work out what that is equals that times 1 minus that, sorry, equals times 1 minus. So that's now calculated partial differentiation of this with respect to this. So what I'm going to do now is I'm just going to multiply those two things together. Which gives me the chain rule to get to there. So we've got that to here. So this bias is just a constant, so I can ignore this sum, which is adding in a constant. If I differentiate that with respect to that, I get something plus a constant, which is just 1, so that can be ignored. We've now got this multiplication of all the weights times the input values. So what I'm going to do, just to make this simpler, is so that we can see all the numbers, I'm going to take these values here and I want to copy those over to above here. So I need to be in row 31. So I'm just going to say equals transpose of this array here. Shift Control Enter again. So you can see all I've done now is to take these values here and paste them across there. And you'll see why in a minute. So basically now I've just got at the top of my table, I've got the output of H30. What I need to do now is I need to differentiate this with respect to this. Partially differentiate this with respect to this. Now this thing here is the sum of all the weights times the bias, so it's the sum of sum of input 1 times weight by the relevant weight, plus 2 things multiplied together, plus 2 things multiplied together, all differentiated out, basically means that we need to differentiate all that, and the answer effectively is the output of hidden neuron 30. Okay, so we've got 3 elements of this calculation in the chain rule. We've got this one and this one, which we multiplied together to get this one. So the gradient of this neuron here equals that times that. So you can see it's a very small gradient. It's 2.89 to the minus times 10 to the minus 9. Now, because that gradient is negative, if you think about a graph with a shape like this, if the gradient is negative, it means that with this side of the graph, to minimize the error, we need to make it bigger. So because this is negative, it means that we need to make that weight bigger. So that supports what we found before, that we found that nudging this value up reduced the error, and nudging it down increased the error. So what we worked out here, by calculating the gradient, is that the gradient is small but negative, which means we want to make that bigger. I'll say that I've probably pressed F9 a few times, and we're probably on a slightly different digit. But anyway, we're probably not on a 0, so that the same thing applies. So that's worked out that gradient there. And what we can do is I can, with the beauty of Excel, I can copy this down 10 times. Well, that's not helping. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. One, two, three. So I can copy that down there 10 times, and I can then calculate this, and I can fix these values so that they can multiply out. So this is that top one, so I need to fix 31. And this one here, I need to fix the AFA. Then I can copy those all down to there. Copy these all the way to there. I'm a bit cozy up till I just up to there, not all the way over to there. Okay, so now we've calculated the gradients for all those weights. Unfortunately, I'm not giving myself quite enough room, so I'm going to shift all this down a bit. Because I've moved it, it's going to keep the same calculation, right? So now I've calculated each of these gradients in this matrix here. Wherever the gradient is negative, it means I need to make that weight slightly bigger, and where it's positive, I need to make it slightly smaller. So that will allow me to then work out new values for these weights. So what I'm going to do is I'm going to copy these down here. So what I'm going to do is, I've already set up over here a learning rate I've called rate. So what I'm going to do is I'm going to use a formula here to say that, so I want this, these are the weights that have been used in the forward pass. These are the gradients, which represent the gradient with respect to that individual weight. Basically, if they're negative, I want to make the number bigger, and if they're positive, I want to make the number smaller. And I'm going to use the rate to kind of control how big that step is. And what I'm going to do is rely on the value of the gradient as well, and say if it's a big gradient, I want to take a bigger step. So I'll use the actual value of the gradient in the calculation. So I'm going to say equals the old weight minus the gradient times the rate. So that will give me a new weight, and that's 0.0462. And that's 0.46. The gradient was positive, so it's made it slightly smaller, 7. 46, is that right? Not quite right. 47, 46. Yeah, so it's positive, so I want to make it slightly smaller. So I made it slightly smaller. It was 0.47 and we made it 46 because the gradient is positive. Okay, so that's the calculation for the new. So I'll paste that over all of those. That will give me the value of the new weights. Okay, so here's the weights, the random weights that we generated. Here's the gradients. Just going to shift that down a bit more. Okay, because these are the copied outputs from the hidden neurons. These are the delta. These are the gradients. And these are the new values of the weights. So what I want to do is use these weights instead of the existing weights in my calculation. But I'm not done yet, because what I need to do first is I need to calculate the same thing here. I need to work out how I improve on all of these weights to make things better. So the same logic applies. What I need to do is calculate the gradient here. Now, what I need to do is to take is to work out how I calculate my entry point. Now, when we in the output neurons, we use the error calculation to work out our starting point. Now what we need to do is we need to work out our entry point into here. So what I'm going to have to do is to work out how this influences what's over here. So I need to know whether adjusting this weight up or down makes the error go up or down. But the problem I have is I can calculate, I know how that gets into that sum. It's the same as we did before. That sum gets added to the bias. That bias is added into the sum to give us the net. We then apply the sigmoid function. The problem is that value there then gets spread through the weights, all these different weights, and then so it's effectively impacting all these numbers here. So adjusting that weight over here will change all these values over here. Now, what do know though is that I know what the gradient at this point here is because I calculated that here. That's these values here. So each of these values here is calculated by multiplying the output of hidden neuron 1 multiplied by each of these weights. And I need to differentiate that with the output of each hidden neuron 1, which gives me each of these weights. So if I multiply each of these weights by these values here, that will give me the gradient with respect to this value here. So let's give that a go. So that needs to be, do that here. So let's give that a go. So I need to take each of the weights multiplied by these values here. Sorry, these values here. So these values here are generally called the deltas, right? Because this is the gradient at the point that we enter the output neuron. So what I need to do is to say that's so I need to take each of those weights. So I need to take the I need 30 of them. I need to say it's equal to transpose of the output weights, the matrix multiplication of the transpose of the hidden weights times these deltas. Okay, so that gives me the gradient of this point here. I've got 30 of them. And then I can do the same thing I did before, right? So I need to use the chain rule and say that that gets me to there. I've then got to differentiate this here, which we said before was equals that times 1 minus that. Which we can split down there, and then we can say that equals that times that. which gives us the deltas for here. Then I need to do the same thing again. We'll bring in, because now that we've got this calculated, it's pretty much the same thing all over. So I need to transpose these. Equals transpose. So let's transpose the inputs again. Got a few too many. Never mind, I'll have to live with that. Then I just need to say that the new weight equals that times that. And again, I need to fix my values so that that's always 34. That's always ADN. Then I can copy those. Which gives me those weights, those gradients, and I can do the same thing again. I can say the new weight equals the old weights minus the gradient times the rate. I need that 30 times. Only 784. Find a better way of doing that. Right, we'll do it the way we did it before. So I just need an easy way of making it 784 by 30 matrix, which I'll do this way. There we go, equals the old weight minus the gradient times the rate. There. So what we've done then is we've now calculated slightly better values for the weights. So that's minus 0.641 minus 0.618. So we've slightly adjusted the weights. So what I'm going to do is I'm going to name these ranges, and I'm going to name this one hidden weights. I'm going to name this one new hidden weights. I'm I'm going to name this one output weights. And call this new output weights. So now I've got my new named ranges. And what I need to do then is I need to copy the new weights on top of the old weights. So I can do that quite simply by using a little macro. So I'm going to create a little macro. Got another version in here. Developer record macro. There we go. I'm going to call it learn. I'm going to give it a shortcut key of L, and I'm going to hit OK. So what I want to do is I want to copy the new hidden weights. Home, copy. Onto the hidden weights. File, oops, home, paste, values, and I want to then go to new output weights, home, copy, and then go to the output weights, paste values, then press F9 to recalculate everything. So then I want to do developer stop recording. So what I've done there is just created a macro which will copy the new weights on top of the old weights for both the hidden and the output weights. I'm not optimizing the biases. You can do. It's just an extra step. It makes it a little bit more complicated. So what I should be able to do now is if I press Control L, Control L, I have to do Shift Control L, Shift Control L. What it's doing now is every time it's doing that, it's copying and pasting those new weights on top of the old weights. So it's gradually improving the weights. Now the problem with doing it this way is that the screen's flashing and I can't really see what I'm doing. So to improve this, I'm going to cheat slightly, and I'm going to go into here and say Edit. So here's this is what it's recorded. But I'm going to just say worksheets. Sorry, worksheets range. Hidden weights. W equals same thing again. New hidden weights. Same thing for the output weights. So this is just a simpler way of doing it, using VBA coded directly rather than the macro. So I think that's right. Worksheet NN range hidden weights equals new hidden weights, range output weights equals new output weights. Alright, new hidden weights, new output weights, and then still with the calculate function on the back of it. Okay, so now if we go back here, we can see that we can go to the control tab. We can reset all this. So now if I do F9, it's just going to calculate new values. But now if I do Shift Control L, what it's doing now is it's bringing in a new number, and each time it's bringing in a new number, it's slightly improving these weights. Let's see that in action. So you can see at the top here where I've just highlighted one weight that it's slightly adjusting these weights. If I keep L held, then you can see that it's adjusting it slightly. So if I just keep doing that for a while, hopefully it's gradually going to keep improving the weights. You can see I've kept it held down, and the weights are creeping up slightly. Sorry, looking at this value here, this is the percentage that it's getting right, okay? So it's now at 12%, so I'm hoping if I keep this pressed for a bit, that number's gradually going to increase. Seems to have stuck at 13%, so I'm just going to pause the video. I'm just going to do a quick review of everything and just make sure I haven't missed something obvious. Okay, I think I found the problem. When I transposed the weights, I chose the gradient of the weights, not the weights themselves. So I'm going to shift that up there. Because if they're array, I have to do the whole thing. Okay, so I haven't tried this, so you'll see the numbers are still the same. So if I now do Shift Control L, give it a bit of time. So what I'll do is I'll pause it again and I'll keep my finger pressed and do a couple of hundred while you're not having to wait. Okay, so I've gone up to 900. You can see that the accuracy rate is now 18%. Now, obviously, that's including quite a few where it was where it wasn't particularly well trained. So if I start again from scratch, you can see we're now up into the 20s. So what's happening now is obviously every time it does an iteration, it brings in a new number. It slightly adjusts the weights so that that new number is slightly improved. Now the danger is it's going to slightly make worse the calculations for the other numbers, which is why having a small rate when we're doing it this way, because we're doing one at a time, is quite important, because otherwise you just end up shifting the numbers too much. So I've got a fairly low learning rate of 0.1 so that it can learn. So we're just going to pause it again and give it a bit more. It seems to have got stuck at 30. Let's see if we can get it past that if we keep going. Okay, so we've sampled 3,000 numbers now, roughly, and it's improving as it goes. The problem is that quite a few of those were done before it was trained properly, so I'll now do it again from here. You can see we're up at actually 50-odd%. Now the key thing here is we're kind of training and measuring it at the same time, right? So remember there are 60,000 samples in the training set, and we've only done 3,000, so the chance of us kind of just learning digits from the pixel pattern directly is quite slim, because the chances of having seen the same number twice is quite low. But it's important generally to have a separate training set and testing set, because you need to make sure your neural network has actually learned a pattern, and rather than just learning the content of the training set. So you normally have a testing set that you can use. So you can see that that's improving. I'm going to pause the video again while we just let it run up a bit more. Okay, so we've run 11,000 now. We're showing 66%, but obviously we've been held back a little bit by the numbers that were assessed when we weren't quite as well trained. So again, I'm going to reset that. I'm just going to reset these values here as well. This is what's called a confusion matrix, and it will tell us which numbers it's got right and which numbers it's got wrong. And I've also cheated slightly, because I've actually put a for loop around here, so I can press Shift Control then L and walk away and leave it while it does 5,000 iterations. So let's give that a go. So the confusion matrix, what this does is this is the number, which way around is it? This is the number that it's this is the answer, and this is the guess. So you can see that it guesses it guesses 15 times when it is a 0 that it is a 0. It's getting everything right roughly about the same amount. Often it's struggled with one number, but it's doing quite well with a 4. Sorry, this is that way around. It's doing quite well with a 1. It's getting a 1 right 100% of the time. It's getting a 6 right 92% of the time, but it's only getting an 8 right 54% of the time. So that's what that number's doing there. So we'll leave that to run for a little bit more and see how it comes out. Okay, so we're up at 16,000 now, up 80%. So you can see across here that it's quite confident with a 1, but it's not so confident with a 5. And you can see that a 5 it's confusing with an 8. And it's not too confident with an 8, and an 8 is confusing mainly with a 5. The 9 it's confusing quite often with a 4. Now you can understand that because they look quite similar, so you have to bear in mind that the image that we're presenting to the neural network is not the image like this. It's just a list of the numbers in a vector form. So the fact that there's kind of loops around the 8 and loops around the 5, and it's confusing them, it's spotting that despite the fact that it doesn't know that some of the cells are next to each other, some of the pixels are next to each other, so it's still managing to work out the numbers and mix up the same ones that we would mix up. Leave it running a bit more. Stuck a bit at 80. Okay, so we're up at 26,500, and we seem to have hit a bit of a plateau. So we'll give it a bit more of a run. I'll reset the values again. Okay, so now we're up to about 40,000 training samples. we've managed to get it to 85%. We've kind of been at 85% for a bit, so we're going to just stop it when it gets to 40,000 and see how it does against the test data. So it's not seen any of the test data. Now obviously we've run more than half of the training sample through the neural network, so to be certain that we haven't just somehow managed to memorize pixel positions and that we've actually learned something. Because I can change that to testing. So what's going to happen now if I press F9? That it's going to pick a value between 1 and 10,000 now, because there's less samples in the testing data. I'm going to reset this and this. So again, these are just using formulas. All these calculations here. There's no VBA apart from the VBA that you've seen to copy the weights from the new weights on top of the old weights. So we'll reset the confusion matrix as well. So we are need to change this. We'll just run it for 5,000 and see how it does on the testing data. Here we go. So you can see it's not been too bad, 83%. We've given it quite a bit of training actually. You can see that it's still managing to get most of them right. 9s and 7s it's struggling with a bit. 8s and 3s. 2s and 7s. So we'll let that run for the 5,000 and see how it does. In the meantime, just wanted to kind of summarize using this diagram what we've done. So effectively we've got an input vector. We've got weights that link the input to the hidden neurons, and we do a matrix multiplication of those two to calculate this. We add in the bias and calculate the sigmoid function, and we use a matrix of weights to link the output of the hidden to the input of the output layer. We do a matrix multiplication again. We apply the sigmoid function and the bias, which gives us an output of the neural network. We compare that to the target, calculate the error. We then, to improve the weight, we back propagate, it's called. We calculate the gradient of this point here. Sorry, the gradient of the error, which is minus the target minus the output. We calculate the gradient with respect to the sigmoid function, which is the output times 1 minus the output. We work out the delta, which is those two multiplied together. We then work out the gradients of the weights, which is the transpose of the output of the hidden neurons times the delta for each of the weights. And we work out a new weight by taking the output, the old weights, and the subtracting the delta, the gradient of the weights multiplied by the learning rate. We work out the transpose of the output weights multiplied by these deltas to calculate the input to the back propagation of the hidden weights, and we again work out the gradient of the sigmoid, this time from the hidden neuron. We multiply those two together to get the deltas, and then we do the same. We transpose the input vector multiply each cell multiplied by the relevant delta. We calculate a gradient of that, and then we work out the new weights in the old hidden weights, subtracting the gradient multiplied by the learning rate, and then we just copy these two new weights on top of the existing weights, and then we run round a new cycle. That's just a summary of everything we've done. You can see this is all basically just matrix multiplication, which is why something like Python, which is very good at matrix multiplication, especially if you use some of the SciPy offerings, which means that Python's very, very good at doing matrix multiplication. So this can be done very, very simply. So let's go back and see how we're getting on. So we got up to 87% on 2,000 or so samples. So a reasonable performance. We could probably train this a little bit more. You could change the learning rate. Sometimes having a smaller learning rate when you get closer to the maximum can be better, because you want to take small steps so you can really get close to that optimum weighting. Sometimes it's tempting to push the rate up, but that can often be counterintuitive or counterproductive. So we'll leave that just for a moment and see what it gets to when it gets to 5,000. I've just realised that it did shift Control L, which means it's actually learning from the training data, from the testing data, which I shouldn't really have done. I should have just kept F9 pressed, because we shouldn't really be training off the testing data. The whole point is you never train off the testing data, you only train off the training data, because then you can measure how well you're doing. But in this particular instance, I don't think it's going to spoil the numbers too much. So let's just let that run until it gets to 5,000. Okay, so we've done 5,000, and we've come out with a learning rate of 87%. Sorry, an accuracy of 87%. So almost 9 out of 10 correct. Now I've got this up to, in other examples, 96%. I think is the best I've done. We haven't trained it a great amount. We didn't optimize the biases. You can change the way you initialize the weights to give you a better chance of finding an optimum set of weights, and we didn't do anything clever with the weights. But hopefully that gives you an idea of how you can create a neural network in Excel using the minimum of Visual Basic to recognize digits. Thank you very much.